Hey, there we are. All right. Well, today, again, I think this is all fun, so just going to have to bear with me. Today, the main topic is going to be all about logarithms. So, logarithms are a different way of looking at exponential expressions, and I love this stuff. Talking about powers make me happy. All right. So I don't know what it is, but a lot of times whenever I bring up logarithms to my students, they don't like this. They're unhappy. They have some kind of past trauma that says logarithms are so difficult. I can't do them. Well, I'm going to stop you right there. If you practice with this, you can do it. So let me try to break it down and make it as nice and simple as possible. So let's start with this. If I have 5 to the third power, now I would like to imagine that all of us here can figure out 5 to the third power. Now, if you're struggling with that, go off to the side and remember what 5 to the third power means. It means that you have 3 factors of the base 5, and if you multiply all of these guys together, 5 times 5 times 5, you would have 125. And so when we have 5 to the third, we have this exponential expression, we know how to work it out. It's just a matter of interpreting that power, using the base, and then doing the math that we have here to get 125. All right, so this equals 125. Now, there is a way of looking at this expression in a slightly different way. So there are times that we talk about radicals, right? So if I ask you to talk about the cube root of 125, when you first saw an expression like this, you had to learn to think about it in a backwards way, almost like you were, reverse engineering the problem. And the way that we would approach this is that we would be thinking, okay, what to the third power equals 125? And then it was our job to figure out what goes in the blank. Okay? So you could look at your list of powers and you would eventually find that 5 to the third is what gives us 125. And so we know that we would fill in a 5 right here, and that's our answer. So the cube root of 125 is 5. Now I want you to see what we are given in this particular problem. You see that highlighted here in blue. We are given the power indicated by the index. The cube root tells us we need to be thinking about powers of 3. We need to be thinking about cubes. The radicand, the number inside, is giving us the answer to the exponential equation that we have up here at the very top. So we're still working within that framework. But for the radical, it wants to know what's the base. Okay, and I think most of us are like, yeah, I get that. I get radicals. Okay. Well, let's talk about logarithms, and we'll see how they are, I'm not going to say exactly the same as radicals, but there is a connection going back to what we have boxed at the top here. So for a logarithm, you would have it written like this. Log base 5 of 125. Now, this expression is asking for a particular piece of information from what we have in the box. The base here, and I do want to make sure we understand that this base is almost like a subscript here for the log. But when we say base, that's exactly what we mean. It's the base. So if I were to write this as an exponential equation, it'd be 5 and then raised to some power. And this is supposed to equal 125. So what we are given from that exponential equation is we're given the base, we're given the answer, we don't know the power. That's what a logarithm is asking. The logarithm is asking, what's the power? And again, as we can see from what we already did over here, we know that 5 to the third power is 125. Which means the answer to the log, the answer to the log is that power is just 3. This is how logarithms work. And I don't want to say that's it, because there will definitely be some other things we have to consider in terms of the powers and the things we're going to see. But in essence, this is all we have to worry about for logarithms, in addition to some other properties that we're going to see here in just a little bit. So if I were to ask you this, what is, excuse me, and there we go, there's the door closing. So if I ask you what is log base 2 of 16, the question that we are asking is 2 raised to what power equals 16? The answer to the log is the power. Now, if you don't know what this is, then you're going to need to build it. So hopefully you know some of your powers of 2, but if you don't know anything, start here. 2 to the first is 2. Well, that's not the answer. 2 squared is 4, so we're just multiplying times another 2. 2 to the third, I multiply times another factor of 2, and I get 8. Please do not say 6. 2 to the third means 2 times 2 times 2. It's all multiplication, it's not addition. And then 2 to the fourth, multiply 8 times 2, and you get 16. And so it's that exponential equation that we have right there, that 2 to the fourth equals 16, that leads me to my answer, which is 4. Right? So for logarithms, the answer to the log is the power. Now, there is another way that we could look at working this problem, but it still requires us to know all of our power stuff over here. Okay, so let me show you another way of looking at this. If I take log base 2 of 16, and we know that we got to figure, okay, so 2 to some power, right? So 2 to, let's call it the x power, equals 16. Well, what you're doing is that you are thinking about this in terms of an exponential equation. And if you look at the video that I streamed yesterday, College Algebra Day 9, you'll see that we go over how to solve exponential equations like this. And in order to solve that, you have to be able to identify the base that's common for both sides of the equation. So 2 is the common base, and 16 is 2 to the fourth power. So that means that x equals 4. In other words, the answer to this logarithmic expression is 4. Another way to ask this is 2 to the what power 16. We should be able to comfortably say 4. If I ask what is log base 6 of 36, somewhere off to the side, you've got to be thinking about this. 6 raised to some power is equal to 36. Again, we should know our powers. If you don't know your powers, then I suggest that you make a list of your squares, your cubes, your fourths, your fifths. Or something else you could do is that you could just take some of our key numbers, like 2, and just make a list of those subsequent powers. So we'd go 2, 4, 8, 16, and so on. All right, so what would you raise 6 to get 36? And the answer, of course, is going to be 2. Again, should be nice and easy. Now, things get a little bit weird when it doesn't seem to be as clear as it is right here. For example, if we were trying to simplify log base 6 of the fraction 1 over 36, you might be thinking, well, there's no way to raise 6 to a power and come up with a fraction. That doesn't make any sense. Well, it does if you remember a couple of things we talked about yesterday. So let me just remind you of this. When you have a base to a negative power, remember that it doesn't give you a negative number. The negative says, put that guy on the other side of the fraction bar. So it's 1 over a to the n. Okay, so that's one thing I want you to keep in mind. The other thing I want you to remember is that if I have a to the 1 over n power, the power that's in the denominator, or the number in the denominator of the power, tells me the index. So a to the 1/nth power is the nth root of a. Okay? And then, of course, what we've seen along with that is if I have a to the m over n, you get the nth root of a raised to the mth power. Greetings, Art. Hope you're doing well today. We're doing logarithms. Yay! But I like logarithms, so what are you going to do? All right, so if I look at this, if I didn't have the 1 over 36, and I just had 36, we would say the answer here is going to be 2. But what kind of power would you have that turns the 36 upside down? Well, that would be having a negative power like that. So just to check this and verify what we're talking about, I am claiming that 6 to the negative second is 1 over 36. And the way that we get that is that we first apply the negative here, and that makes it 1 over 6 to the positive second power. Okay? Again, the negative power does not mean a negative number. It means you do the reciprocal. And so when we work this out, we get 1 over 36. Right? This is how we work with this particular logarithmic expression. And we can keep on doing this. If I say, what is log base 2 of 1/8? Well, log base 2 of 1/8, don't worry about the 1 part right now. Worry about the 8. What power of 2 gives you 8? And you'd be correct to say 3. And then I follow up and say, all right, yes, 2 to the third is 8. But how can I have my power put the 8 in the denominator? And that's if I have a negative power. Okay, so again, keep in mind that when we do logarithms, the answer to the log is the power of the base. Okay, and again, as I read this, you got to make sure that you read things correctly here. Log base 2 is how you read this. Don't say log of 2, don't say log 2. It's log base 2. So when you say base 2, that should be solidifying in your mind that we've got to be thinking about an exponential expression whose base is 2. Oh yeah, I'd love a playlist on linear algebra too if I had the knowledge for that. I don't know. Got a lot of things on my plate to think about, and right now linear algebra is not so high on the list, but I'll think about it. I'll make a mental note and do some research on that. I appreciate that. All right, so let me change things up just a little bit here. Let me just remind everybody watching at home. If I say log base 5 of 25, what's the power of 5 that gives me 25? Okay, it's 2. No tricks here, it's just 2. Okay, I wasn't trying to trick you on that. Now it's this next part we're going to watch out for. Log base 5 of the cube root of 25. Okay, so in order to work these guys, you have to know how to work with the powers, and especially these little properties that I wrote over here on the right side, right? So first, ignore the radical and worry about what's inside your radical. Worry about the radicand at 25. What power of 5 gives you 25? We just answered that in the previous question, and that's going to be 2. But what would you have to see for a power that gives you the cube root? How do we end up with a cube root? Well, check what we did over here. The index for your radical indicates the denominator for your power. And since the answer to the log is the power, that means that this index is going to be the denominator of my answer. So it's going to be 2/3. The 2 is there because 5 squared is 25, and the third is there because we're talking about a cube root. So let's just check this to make sure that you believe me. I mean, I believe me, but I'm just me. What do I know? So if I do 5 to the 2/3, what does that expression mean? Well, look at what we have right here. The denominator tells me I'm dealing with the cube root of 5, and the 2 would go there. Now, you could do the 2 outside the radical. It doesn't really matter, but for right now, I want to put it on the inside because this is going to make a little bit more sense to how it compares with our problem, the cube root of 25. So yeah, we can see that it does work out, and the 2/3 is going to be our answer. Now, there are some things I want to point out here when it comes to logarithms. And don't worry, we're going to be coming back and doing a lot more of these. Remember when we had our exponential function. The exponential function looked like this. It said f of x is equal to log. No, oh my gosh, where am I? I'm not here today. It's f of x equals a to the x. And we had these conditions on here. We said that a has to be positive and a could not equal 1. Well, a logarithmic function is going to be very similar in terms of its restrictions. We're going to say log base a of x. And I think we mentioned this. No, we didn't. Who did I mention that to? Maybe that's a dream. So the base here has to be positive, and it cannot equal 1. So the restrictions on the base has to be the same. Positive and cannot equal 1. So when I've got the log base a of x, we're only going to consider the base there being positive and not equal to 1 because of how the logarithm connects to the exponential function. Okay, and in fact, what's going on here is that the logarithmic function, this is the inverse of our exponential. And the exponential is the inverse of the logarithmic function. So remember with the exponential function, when we were talking about this yesterday, we said that the domain was all real numbers, and we said that the range was from 0 to infinity. Because when we looked at the graph of this, you had this horizontal asymptote of y equals 0, and your typical graph would look like this, where you start off really small and then you blow up as you go out to one side. We talked about the key points that we would see here, and those key points were plugging in -1 gives you the reciprocal of the base. 0 will always get you 1, so that became our anchor point. And if we plugged in 1, we would get a. All the key information that we have for the exponential. Now, if this logarithmic function is the inverse, we already know a lot of information about this guy. So, the domain for the logarithmic function is going to come from the range of its inverse. So my domain is going to be from 0 to infinity. My range is going to pull from the domain of the inverse, so that's -infinity to infinity. Instead of having a horizontal asymptote, we have a vertical asymptote of x equals 0. So the thing with inverse functions is that x becomes y, y becomes x. So when a function has a horizontal asymptote, his inverse is going to have a vertical asymptote. And of course, vertical lines are going to be x equals whatever. For the key points, you're going to take all of these points that you have over here, and again, remember, x becomes y, y becomes x, so they get flipped around. So instead of having the ordered pair -1, 1 over a, we would have 1 over a, -1. Then we would have 1, 0, which is going to act as our anchor or key point. And then we'll have a comma 1. So I just want to do an example of this so you can see what I'm talking about. Actually, I'm going to come over here and grab this so we can examine the graph of this guy. Excuse me. All right, so let's do log base 2 of x. Now, I could pick any kind of base that I wanted to, but doing a base 2 is going to allow me to get a lot of nice points on here, so that's why I'm going to focus on that. Your key points are supposed to be, well, before we had -1, 0, 1 for the x, and now we're going to have -1, 0, 1 for the y. And those key values are going to be the reciprocal of the base, 1, and then the base itself. But for us, we're talking about the base being 2. So 1/2 and 2. So think about what that looks like if we were to write that out in an expression. If I have log base 2 of 1/2, what power of 2 gives you 2? Well, that's power of 1. But what makes it in the denominator? That's going to be a negative. If I jump down to this last one, log base 2 of 2. What power of 2 gives you 2? And that's just going to be 1. And I think the one that gets a lot of students is when I do this, log base 2 of 1. And they go, wait a minute, how can you raise 2 to a power to get 1? Don't forget that anything other than 0 raised to the 0 power is going to give you 1. So what power could you apply to 2 to get 1? 0. All right. Now, we've also talked about, like I said up above, that we have a vertical asymptote of x equals 0. So let's go ahead and put that in play here. So here is my vertical asymptote. So I cannot cross this. I've also said that my domain is going to be from 0 to infinity. So don't try to put any negatives over there. We can't do that. Because you can't take, say here, a base of 2. You can't take 2 and raise it to a power to get something negative. 2 to a power is going to be positive, really no matter what you do. Let's see if I can find that back over here. Nope, we did a lot of fun stuff yesterday, didn't we? Yeah, so if you look at your base exponential function, like this guy right here, you look at your domain. We could plug in anything we wanted to for this guy. But the range was 0 to infinity. There was no power that you could apply here that's going to give you a negative outcome. As you go one way, you get larger and larger powers of 2, so it blows up to get a really big number. As you go towards the left, you're plugging in smaller numbers until you get to the negatives, and we start plugging in negative numbers, you start getting very, very tiny fractions. Now, it approaches 0, but doesn't get to cross that. And so that's why we have a graph here that kind of looks exponential, but it's like it's been flipped and rotated a little bit. So let's plot these key points. We have 1/2 is going to give me -1, 1 gives you 0, and 2 gives you 1. Now, some teachers might say, this is all you need to do, and then connect the dots and blah, blah, blah. We're going to do better than this. Right? So for the exponential, whoops, over here. For the exponential, every step that I moved along the x-axis, I was multiplying times the base to get to the next y value. So you see here I went from 1 to 2 to 4 to 8. Every step I made along the x, I was doubling the y. Over here, we're going to kind of flip that mentality. So every step I go up, I'm going to, because my base is 2, I'm going to double the distance from that vertical asymptote. So you see here that we have a distance of 1. Here is a distance of 2. If I go up one step more, I should have a distance of 4 from this vertical asymptote. If I go up another step, I'll be out here at 8. So this distance from that vertical asymptote is going to be 8 units. And so as I go over, I'm still going to be increasing. Like, he's never going to be flat. He is going to keep getting higher and higher. But the problem there is that it's going to take a really large number for him to go up each successive unit. So, when I plug in 8, I get 3. The next nice point that this guy has is you'd have to go all the way up to 16 just to be up at 4. You'd have to go up to 32 and you'd be up 5 units. So it's taking a very, very long time to grow. And for it to go from 5 to being 10 units tall, you'd have to go all the way up to 1024. So that's a pretty big jump. But look at it as you go backwards. If I go down, I'm dividing by that base. So 8 divided by 2 is 4, divided by 2 is 2, then 1, 1/2, 1/4, and so on. So these guys are going to get closer and closer and closer to that vertical asymptote, but you don't get to touch that. You don't get to cross it, and you got to look just like this. So I hope from here that we can see that our domain, as stated on the other page, or I guess up above here, the domain is 0 to infinity, not including 0. The range is going to be from negative infinity to infinity. And we've got this vertical asymptote of x equals 0. All right? Now, I can choose a lot of different bases here for my log. I like to choose 2 because I get a lot of nice points, and it's a fairly easy graph to do. If I had chosen log base 10, okay, you would still have this guy right here. So this is what I'm going to call our anchor point. Because no matter what our base is, no matter what the base is for the logarithm, we're always going to plot that point first, 1, 0. He is the linchpin for everything here. But if I had log base 10, that means every time I go up 1 unit in the y direction, I've got to multiply my horizontal direction by 10. So that means if I went up 1, I'd be all the way over here at 10. If I go up another one, I'd be way over here, off the grid, off the page, and I'd be at 100. Yeah, so it makes things definitely a little bit more difficult to graph. But tell you what, let's do another one of these, and let's do some transformations and see what we get. All right, so let me do f of x is equal to log base 2 of x plus, let's say 4, and let's do minus 3, and let's see what happens here. So before you do anything, you have to know the shape. You have to know what everything here means. The plus 4 and the minus 3 don't tell you the shape, they tell you how things have moved. My shape is a vertical asymptote and something that looks kind of exponential going up along it like that. Now, the plus 4 on the inside means I do the opposite of what I see, so I'm going to go to the left 4 units. The minus 3 is outside of the log, and we do exactly what we see in a vertical direction, so that means we would go down 3 units. All right, now, the left 4 and down 3, I want you to think about where that new anchor point is going to be. The original anchor point was going to be right here at 1, 0. So let's take that guy and move it left 4 units, so 1, 2, 3, 4, and then down 3. 1, 2, 3. That's going to be our new key base point, anchor point, whatever you want to call it. Now your vertical asymptote started off at being x equals 0, but we grabbed this guy and we shifted it to the left 4 units. So now my vertical asymptote is going to be over here at x equals -4. All right, so my vertical asymptote is x equals -4. Now, if you want to, you can just kind of lightly dash out what should be our new x-axis. And then from here, we plot the rest of the points. Having a base of 2 means every step I go up, I'm going to double my distance from that vertical asymptote. So this is 1 unit. I go up 1, I'm going to double that to get 2. Double that, I'm going to be over here at 4. Double the 4, I'm going to be here at 8 units over. If I went up another unit, I'd be at 16. So that is not going to fit on my grid. But I should have a good sense of where that's going to be. So from this vertical asymptote to the edge of my graph here is 14 units. So 2 more units and I'd be up like 1 unit. So that's kind of where I'd be aiming as I go off the page. Okay. Well, let's connect the dots and see what happens. I also have this half point down there. All right. So a nice logarithmic curve. Please make sure that you don't confuse this with the other graphs that we have. And then here on the left, we're going to get really, really close to that vertical asymptote. So the same graphing techniques that we've seen before will apply to this. Okay. Now, because I shifted left here, that's going to change my domain. So it started off as being 0 to infinity, and we moved to the left 4 units. So it's going to be from -4 going all the way to the right to infinity. And my range is going to be, again, all real numbers. And that's going to be the case for all of these logarithmic functions that you come across. The range is going to be all the way to the bottom, all the way to the top, so all real numbers. Yeah, and so, there you have it. And again, we could change the base to something else. I like to keep a base of 2, but just know if I did log base 3, it would look very similar to this, except every step I go up, I'd be multiplying times 3, so I'd be, really, it almost looks like I'm kind of flattening that out. But keep in mind that it never goes completely flat. It is still increasing the whole way. Excuse me. Now, let's talk more about these logarithmic expressions. Oh my goodness, why is my nose itching? All right, so we have something called the common log, or the common logarithm. And the common logarithm is just this expression. And we'll just say log of x. If you see log and there is not, if there's not a base that is explicitly written, this is understood to be log base 10 of x. So this common log is used in all kinds of things. We're talking about measuring how loud noise is using decibels. The Richter scale, I think it's kind of been modified now, so it's not exactly the Richter scale. I'm measuring pH balance. All those guys are measured in powers of 10. And so using a common log that is also dealing in powers of 10 makes a lot more sense. And sometimes you may see graphs when you're looking at data, and they use what's called a logarithmic scale. So typically when you look at graphs, you have these tick marks that are evenly separated, right? And you just go 1, 2, 3, 4, 5. But on a logarithmic scale, I guess I better write this here, right where my face is not in the way. And let's just pretend this is M. So for a logarithmic scale, you would have where this is 1, 10, 100, 1,000, 10,000, and so on. So as you're going up this scale, each successive tick mark in the Y is measuring another power of 10. So it goes from 1 to 10 to 100, 1,000, 10,000. And what it does is it takes what would be typically a nasty looking exponential curve and it makes it look a little bit more linear. They don't do this with everything, but with certain data where you are dealing with very, very large numbers on one side and very small numbers on the other side, it's just a way to represent the data so that it kind of fits nicely on there. But again, you've got to make sure that you are able to see what the scale is and that you understand what it means. Okay, so that is the common logarithm. Again, we see this guy a lot in math and science. And then we have this one, the natural log or the natural logarithm. For the natural logarithm, you're going to see it written as two letters L and N. Okay. Now, whenever I write the natural logarithm, I use cursive L and N like this. So natural log x. And with a natural logarithm, we're talking about log base e of x. So let me show you something we talked about. We talked about the other day, right? So here on the graphing calculator, if you look here on the left, you see log and you see ln. Okay, this ln is connected with e to the x. So if you ever forget what does natural log mean, it's connected to having a base e. Log right here means base 10. Okay, so this is 10 to the x. All right, now let me see, what mode am I in? So I'm in classic mode. Even if I'm not in classic mode, I'm in math print mode. If you press natural log, it does the L, N, and it opens up parentheses. If I do common log, it opens up parentheses as well. So always be sure that you know where your parentheses are, where they start, and where they end. Now, for example, if I do the log of 1, so if I do log of 100, we're talking about what power of 10 gives me 100. And of course, 10 squared is 100, and the answer here is 2. Now, if I do natural log of 100, I'm not going to get that answer, because you would see that, e to the second power is not 100, right? Because if I did e to the second power, I get some crazy decimal, 7.389, right? But if I do e raised to the answer they gave me here, 4.605170186, then I get 100. Okay, so please make sure you know whether you're using log or natural log when you're working these problems, so that you don't make some kind of careless mistake. All right, let's see, what else? We have this thing called the theorem on inverses. So right now, this is really just like I'm dumping all kinds of information on you, and then we're going to start using it. All right, theorem on inverses. So this kind of goes to what we said before, how logarithms are the inverses of exponentials and vice versa. So if I do log base a of a to the x, I get x. Or if I have an exponential expression, base a, raised to log base a of x, that would also give me x. So I don't want you to say, oh, these guys cancel each other out. It's because they're inverses. And if you look back to what it means to be an inverse, if you plug a function into its inverse, they will undo each other, and you'll just have whatever that input value was. For example, if I have log base 7 of 7 to the 8th power, I do not want to figure out what 7 to the 8th power is. I could, I just don't want to. But notice the base of the log and the base of the expression on the inside are exactly the same, so we should be left with just that power, which is 8. An example for this other guy here, if I have 5 raised to the log base 5 of the square root of 47. Again, the bases are the same, so these guys are going to kind of cancel each other out. They're not going to cross out or anything like that. They just kind of reduce away their inverse operations of each other, and here you'd be left with the square root of 47. Now that is an exact value. Okay? Don't try to type it into your calculator and come up with some kind of decimal approximation. You only do that whenever the calculator or whenever the question asks you to do that. Right. Now let me show you one of my favorite things. One of my favorite things is called the change of base theorem. I'm going to show you why this is nice and how it can save us a lot of time as long as we are paying attention. Change of base theorem. It says that if you have an expression that says log base b of a, you can rewrite this as the quotient of two logs, log a over log b, provided that you pick some common base. So let's call that base c. Now please notice that the base is the piece that you see in the denominator there, log base c of b. Now since we can pick any base that we want to, we could just do base 10, and so you can say simply log of a over log of b. Or you could use the natural log and say natural log of a over the natural log of b. So we could like throw things into the calculator, but sometimes we don't need to go that far. And let me show you what I mean by that. If I want to find log base 25 of 125, I've got two ways of doing this. And we're talking about not going to a calculator. One of the ways is to imagine that this is equal to some answer, which of course it's going to be. And we rewrite this in its exponential form, which means 25 is my base. X is supposed to be the answer to the log, which is my power. And so I can rewrite this as 25 to the x power equals 125. And now you have an exponential equation that we should be able to solve. You identify the base that's common for both of these, at least that's what we're doing now. And the common base here is 5. So 25 is 5 to the second, then to the x. 125 is 5 to the third. And then when we talked about solving these guys the other day, as long as we have the same base on both sides, we can equate these powers, which means 2x equals 3. Divide both sides by 2, and you get 3 halves. Done. But there is another way that we can do this, and that's by using the change of base theorem. Now, in order to do the change of base theorem, you still have to be able to think about the problem the way that we did here on the left side. Is there a base that's common for 25 and 125? We already know the answer is yes, and that common base is 5. So the change of base theorem up above says I can do log base 5 of 125 over log base 5 of 25. As long as I choose the same base for both of these, it's going to be okay. And by rewriting it like this, I mean, this should be child's play right now, right? So what power of 5 is going to give me 125? Well, it's going to be 3. And in the denominator, what power of 5 gives you 25? That's 2. And you end up with the same answer that we had before, just with a lot less work. So it still means you have to know what those powers are. Now, let me show you what this looks like in the graphing calculator. Now, I don't need to do the graphing calculator, but I want to make sure you see how we can do this. Okay. So in the calculator, we can do log of, we had 125. Make sure you close your parentheses, and then divide by what's in the denominator, which is log of 25. If we've done this correctly, it should give us 3 halves, which is going to be 1.5. Now, also keep in mind that when we were doing the change of base theorem, we said it could be any base that you wanted it to be, as long as it was the same. So if I do log in the top and bottom, that's log base 10. if I do natural log with base e, still the same base, I should still get the same answer. And I do. I think that's pretty cool. Now, I'm not really going to be throwing things into the calculator unless I absolutely need to. For this problem, I didn't need to. So let's think about how we would evaluate an expression like this. Let's say log base 16 of 1 over 32. Now, I hope that we can look at this and see that there is a base that's common for both 16 and, now it does say 1 over 32, but really for all practical purposes, it's just 32. The common base here is 2. So let's rewrite this as log base 2 of, now you got to do the guy that's inside the log in the numerator, over log base 2 of 16. So remember, the base is going to go in the bottom. All right, and now let's work these guys out one piece at a time. So in the numerator, what power of 2 gives me, first of all, what power of 2 gives me 32? And we've already seen today that that's going to be 5. But it's not just 32, it's 32 in the denominator. So that means negative 5. In the denominator, we have log base 2 of 16. And again, go through your powers of 2, and you see that 2 to the 4th is 16. There you go. Done and done. Again, not a whole lot to worry about doing there. If I do log of, let's say log base 81 of 27, is there a base that's common for both of these? Again, look at your powers. Now we know that's not going to be based on a power of 2. And maybe you've gone off to the side and you've got your list. You say, okay, well, I got 3 to the 1st is 3. 3 squared is 9. And maybe you've worked this out, use a calculator, I don't know. But you at least have these powers at the ready so that you don't have to spend a whole lot of time figuring what these guys are. And hopefully the more you see it, the more it kind of gets stuck in your mind. So I hope here that you can see that both these guys have a common base of 3. So I'm going to rewrite this as log base 3 of 27 over log base 3 of 81. And using the work that I see there on the right side, log base 3 of 27, remember the answer to the log is the power, so that's going to be 3. And what power of 3 gives me 81, and that guy is 4. So again, should be a fairly simple thing to do as long as you know your powers. Now, again, it could be that you don't like doing that change of base theorem and you say, I would rather not. Can I look at this as an equation, just say let it equal x? Sure. Then you have to rewrite this as an exponential equation. 81 to the x equals 27. So 81 to the power of x equals 27. And then figure out what the common base is. Again, you've got to know the common base is 3, or else you can't do this. You couldn't have done the last part. So 81 is 3 to the 4th power raised to the x. 27 is 3 to the 3rd. All right, so power to power means we multiply. And now these guys have the same base. So we end up with 4x equals 3. Divide both sides by 4, and you end up with 3/4, which, not surprisingly, is the same answer that we had the first time you did it. Yeah, and so it's working with logarithms. Now, let's take these and do something a little bit more exciting with them. and let's solve some equations that contain logs. So if I have log base 5 of 7x plus 2 equals 3. So I have x that's stuck inside of a logarithm. Now I want to make sure it's very clear where x is and what kind of equation we have. We don't have something that's quadratic. We don't have absolute values. We don't have fractions. We don't have radicals. We have something that's logarithmic. And one of the main things that we do here is that we have to solve by rewriting this as an exponential equation. So your base is 5. The answer to the log is the power, and that's supposed to equal what's on the inside. So this becomes 5 to the third is equal to 7x plus 2. So in one quick little step, we lose the log, and we have a much easier equation to tackle. 5 to the third is 125, and now we have a linear equation to solve. So we do this simply by moving 2 to the other side. So we have 123 equals 7x. And that means that x is equal to 123 divided by 7. Now, it'd be great if this guy could simplify even further, but it can't, so we're just kind of stuck with that. But yeah, that's all there is to it. There's nothing more for us to do for that problem. It's almost kind of boring because it's too easy, right? But what if we make things just a little bit more complicated? If I have log base 3 of, I'm gonna mess this up. All right, we'll see what happens. So let's say 2x squared minus 9x plus 18 equals 2. All right, so I know that there's that little quadratic thing that we see, but it's inside of the logarithm. So the main guy here is a logarithmic equation. Now let's rewrite this so it's not logarithmic anymore. So my base is 3, and my power is 2, so let's make that connection. So 3 to the second power equals 2x squared minus 9x plus 18. And now you have a quadratic equation to solve. All right, so this is, of course, 3 squared is 9. And because this is quadratic, we want to make sure we get everybody to the same side. All right, so let's see, we have 2x squared minus 9x plus 9 is equal to 0. All right, so let's think about how we solve quadratic equations. The first thing we try to do is use the square root property, but we have x in 2 different terms, so the square root property doesn't work. The second thing we try to do is to factor. Now, for factoring, we would consider the AC method. I think that's one of the easiest methods to think about. So multiply the leading coefficient times the constant, 2 times 9, which is 18. And then we try to find factors of 18 that have a sum of 9. If we can do that, then we've got something that can factor. And it shouldn't take us too long to realize that 18 can be broken down as 3 times 6. And so those are the numbers that we're going to be thinking about in the factoring process. Now, if you've forgotten how to factor, I suggest you go back and look at my live stream that I did College Algebra Day 1, I think it was Day 1, when I went over some of the basics of factoring. So what we can do is we can rewrite this middle term using 3x and 6x. and then make sure that you get the correct sign so that things will combine correctly to give you the negative 9x. So both of these guys are negative. Now, we factor by grouping. In the first group, the common factor is x, and we have 2x minus 3 left over. In the second group, we lead off with a negative, and the common factor for 6 and 9 is 3. So if we factor or divide those guys out, we'd have 2x minus 3, and now we can finish the factorization. So 2x minus 3 times x minus 3 is equal to 0, and then we solve this. So from this first factor, x equals positive 3 halves. From the other factor, x equals 3. Now, both of these guys should work. I don't see any reason why they shouldn't here, because I know because I made the problem, I know how it's set up. If we were to plug 3 or 3 halves into this quadratic and work it out, it's going to equal 9, because that's what we said right here. In this statement, we said, okay, the inside stuff here is going to have to equal 9. What values will make it equal 9? 3 and 3 halves. And if you do log base 3 of 9, you would get 2. So both of those values when plugged in would turn the quadratic into 9. Log base 3 of 9 is going to be 2, so we know things are going to check out. Things don't always work out that nicely, though. But before we do that, there are some other properties, some other things we have to talk about when it comes to logarithms. All right, so here are some properties of logarithms you must know. All right, properties of logarithms. So this is for a, x, and y being positive. A does not equal 1. Yeah. So we have this first one here. It says log base a of the product x and y can be split up to be log base a of x plus log base a of y. So if you have a product inside of a log, that gives you the sum of logs. In a somewhat similar fashion, if I have a quotient inside of the log, that's going to give me the difference of logs. So this guy right here. So multiplication inside is going to separate to give you sum of logs. A quotient inside of a log is going to give you the difference of 2 logs. Now, we're talking about how these guys split up, but you could also combine them if you look at it going back over here. So this does go both ways because it is a property. The other one is this. Log base a of x to a power gets rewritten as r times log base a of x. So for that power, we just bring it out in front. Now, how do we use these guys? Well, if I have log base 2 of x to the third, I can take this power that I have inside the log, and I can write that out in front. So this becomes 3 times log base 2 of x. Okay? Powers can come out directly in front. Or if I have, let's say this, if I have the natural log of a to the 4th times b. So I do see a power on the inside. However, I can't just bring that out in front of the log. I must first deal with the issue that I have a product on the inside. So this becomes the natural log of a to the fourth plus the natural log of b. Once I have it split up like that, then yes, I can bring the 4 out in front of this particular natural log. So it becomes 4 times the natural log of a plus the natural log of b. Because that power of 4 is only connected to that factor of a, not b. So it makes sense that whenever I split it up with these two different logarithms, that the 4 is connected to the natural log of a, not the natural log of b. In much the same way that we can split up these expressions, we can also put them back together. If I have 5 times the log of x plus 7 times the log of a, I can't put these guys together just yet, even though there is addition. And that's because of the coefficients. So I can use this property of logarithms right here and go backwards with it. Take the coefficient, and that's going to become the power for what's inside the logarithm. Same thing here for the 7. So this gets rewritten as log of x to the 5th plus log of a to the 7th. And now, because of the sum here, we can put these guys together inside the same logarithm. We do that as a product, so x to the 5th times a to the 7th. Let's put those guys inside together like that. If, however, I do this, if I say log of b minus 3 times log of y. So I do have subtraction, so I should be thinking about having a quotient at some point. But first, let's address the issue of the 3 that's out here in front. That becomes a power for what was on the inside. All right, so this is log of b minus log of y to the 3rd. And now we can bring this together as a single logarithm. B is in the numerator, and y to the 3rd is in the denominator. In fact, anything that has a negative coefficient really means a negative power. So here's another way I could have written this. I could have written this as log of b plus, I know it says minus, but watch this, I'm going to say plus log of y to the negative 3rd. So if I grab not just the 3, but also that sign, that negative, it becomes log of y to the negative 3rd. And again, you might be saying, well, now this is different because this is multiplication. Well, yes, because there's a plus here between the two logs, I'm going to bring things together through multiplication. So that's b times y to the negative 3rd. But we don't leave negative powers in our answers. And the way that we would fix this is by remembering that a negative power is going to put that as a reciprocal. It's going to flip that over. So we end up with b not times y to the negative 3rd, but divided by y to the positive 3rd. So you see we have the same answers. Just a slightly different way of looking at it. Now, that being said, let's take a look at this problem. If I have log of, let's say log of x plus 4 plus log of x minus 5 equals 1. So an equation is solved, but now I've got two logarithms here to worry about. We just got done seeing properties of logarithms that will allow me to take this sum of logs and turn it into a single log that has the product of these two pieces, x plus 4 times x minus 5. That is a legitimate step here. Now, the thing we want to remember is that we're dealing with the common log, so there's no base that is explicitly written, but we do understand that it's base 10. So we want to rewrite this from a logarithmic equation to an exponential one. So 10 to the first power is equal to all the stuff on the inside. So 10 to the first equals the product x plus 4 times x minus 5. All right, seems like a simple enough equation. Let's work this out. All right, so we have 10. Here on the right side, if you FOIL this out, we have x squared minus 5x, then distribute the 4. So plus 4x minus 20. So definitely have something quadratic here. Let me go ahead and move this 10 to the other side by subtracting it. All right, so we have x squared minus x minus 30. I'm going to put the equal 0 on the right side. It just feels better that way. All right, so we have something that's quadratic. We can't use the square root property because we have two instances of x. But hopefully we can factor this guy. So the x can break down as x times x. You want to be thinking about finding factors of 30 that have a difference of 1. And those factors would be 5 and 6. We just have to make sure that we get the right signs here. So we know they have to be opposite signs to multiply to get a negative 30. And you want to be able to combine them to get a negative 1. So the larger of these two has to be the negative 1, and the smaller one is going to be positive. Solving this means that we have x equals negative 5, or on the other part here, x equals positive 6. Now, there's this temptation to circle both of these and then go on to the next problem. But we've got to be careful because of the way this problem was written originally. See how these logarithms are written separately? This really messes with what our domain is. And it's a lot more restrictive than what we saw over here. Over here, the two answers we got, perfect, not a problem. But now we need a check. All right, so let's check this guy. Now, if you see what we had up above, we need to check this. Log of, it was x plus 4, so negative 5 plus 4. The other part was log of x minus 5, so this is negative 5 minus 5. We want to see, does this equal 1? Well, we end up with log of negative 1 plus log of negative 10. The problem with that is that both of these guys are undefined. The domain for log, for any log, it has to be positive. You can't plug in negative numbers into the log. Now, you can get out negative numbers, but you can't plug them in. So yeah, we have something that is undefined. Well, let's check this other one. So I'm going to do 6 plus 4 inside one log. Oops. And then I have 6 minus 5 inside of the other. So we have log of 10 plus log of 1. Log of 10 is 1. Log of 1 is 0. So it equals 1, which is what we wanted to have. Now, the reason that we only have one of these working as a solution is because of how the original problem was written. If this were the original problem, you could plug in both negative 5 and positive 6, and they would both work. The reason they'd both work from this point is because you would have to deal with the multiplication first before you apply the logarithm. So if I were to plug -5 in here and in here, you would end up with -1 times -10, which is +10. And you can do the logarithm of that. But that wasn't my original equation. This was my original equation. And this guy had certain restrictions on the domain we had to watch out for. This guy means that x has to be greater than -4. So x plus 4 has to be greater than 0. And this one says x has to be greater than +5. So this is the more restrictive of those two domains. So any answer you have has to be greater than 5. If it's less than 5, then it's going to invalidate, it's going to give you an undefined expression for that logarithm. And you see that the answer we got here was -5. So that guy is less than 5. It doesn't satisfy either of those, does it? But you look at 6. 6 does work for both of those. It doesn't give you anything that's going to make the logarithm undefined. So that's why that is the one and only one answer that we have here. All right. I feel like there's something else that I wanted to talk about, but it's just not clicking right now for that. Yeah, but in essence, that is, that's logarithms in a nutshell. Now we can, I remembered what it was. So smart. Now, sometimes we need to use logarithms to help us solve certain equations. So let's look at something that we would have looked at yesterday. If we need to solve something that says, let's say 4 to the 5x plus 2 equals 8 to the 6x minus 7. We identify a common base, and then we are able to quickly solve this, right? So this is 2 squared to the 5x plus 2. 8 is 2 to the 3rd to the 6x minus 7. Power to power on both sides, so we multiply. That's 2 to the 10x plus 4 equals 2 raised to the 18x minus 21. These guys now have the same base. Everybody's happy. We get a nice linear equation to solve. Right? Aren't we happy with that? I would subtract 10x so that I have a positive coefficient. And let's move the constants to the other side, so I'm going to add 21. And now we have 25 equals 8x, so x equals 25 over 8. Nice and easy. Nothing crazy going on there. We identify the common base, and we're good to go. But things don't always look that way, do they? Sometimes we have equations that look like this. If I have 2 to the x is equal to 5. Well, with 2 and 5, you can't find a base that's common. And before you start saying, what about 1? See, 1 is a common factor, but it's not going to be a common base because you can't rewrite 2 as 1 to a power. This doesn't work because 1 to any power is going to be 1. So instead, here's what we're going to do. We're going to do this little trick called applying logs on both sides. Now, it doesn't matter if you use common log or natural log, but we're going to do this. I'm going to do the natural log of the left side and the natural log of the right side. So we end up with an equation that looks like this. Natural log of 2 to the x equals the natural log of 5. Now, do keep in mind that natural log of 5 is just a number. You could type it into your calculator and you get some decimal and you're done, right? On the left side, it's a little bit more complicated. But notice that we have x in the power, but now it's inside of a logarithm, so we get to use a property that we mentioned a couple pages ago, that a power on the inside gets to come outside in front of the logarithm. So this becomes x times the natural log of 2 equals the natural log of 5. Natural log of 5, we said, is just a number. So is the natural log of 2. So since we want to get x by itself, you divide by the natural log of 2. So these guys are going to reduce, and that gives us just x by itself is equal to the natural log of 5 over the natural log of 2. And that's it. This is an exact answer using expressions that we have readily available on most scientific calculators. Now, we can go to a decimal approximation, but we've got to go back to the calculator to do that. The thing to be aware of is using your parentheses correctly. So if I do the, let's clear this out, if I do the natural log of 5, I've got to make sure I close that off as soon as I'm done with that particular logarithm, divided by the natural log of 2. All right, so I get an answer that is approximately 2.3219 if I round to 4 decimal places. Now let's see how that works with my original equation. So I'm saying this is my answer to the question, 2 to a certain power is going to give me 5. So 2 raised to the 2.3219. Now I did round, so I know it's not going to be exact, but you see that that's pretty close. 4.9999. That's really close. And if I were to change this just a little bit, 2.3219, let's round to 5 decimal places. So I get 5 with a little bit of extra stuff over here. Let's add one more level of accuracy, and let's go out here to 6 decimal places. I did not type a decimal. I sure didn't. Ooh. I gave a number that was way too big for the calculator to work. Wait, what did I... Oh my goodness gracious. I'm not typing the numbers correctly, am I? 2 raised to the 2.321928. All right, so that's getting even closer and closer to the actual value that we're looking for. Now, for a lot of things, it's going to say round to the nearest thousandth or round to the nearest 4 decimal places, so make sure you read and respond correctly for that. Now, I used natural log here. I also could have used the common log. Let's see, does that make a difference? If I do log of 5 divided by log of 2, again, paying very close attention to close off those parentheses. And I get the same answer that I had above, the 2.3219. All right. Now, again, these problems can get more and more difficult, but it's just adding steps. It's nothing to really freak out about. So let's do this. If I do 3 raised to the x minus 5 is equal to 7 to the x. Well, 3 and 7 do not have a common base. So what do? Well, we do what we just did, and we apply log on both sides. Again, you can use common log or natural log, but you have to be consistent. Whatever log you apply on one side, you have to apply the same log on the other side. So I'm going to do this, the natural log on the left and the natural log on the right. And again, the reason that we're applying the logs is so we can use that property of logarithms that will allow me to take the power inside and bring it out in front. Now on the left side of this equation, you have two terms of there. You got x and minus 5. So when you put that in parentheses and say x minus 5 times the natural log of 3, and then on the other side we have x times the natural log of 7. So again, let me remind you, those pieces are just numbers. You could go to your calculator, type them in, it's going to give you a decimal. It's going to be a messy decimal, but it is a decimal. Now, we don't actually want to do that right now. You don't want to have those decimals running around in your problem because to get an answer that's going to be accurate to the required number of decimal places, you're going to have to write a bunch of those numbers over and over again. I'm not going to do that. I'm going to keep it nice and simple. But again, I want to keep in mind that it is just a number, which means on the left side, I can distribute, just like I would distribute anywhere else. So this gives me x times the natural log of 3 minus 5 times the natural log of 3. Make sure that you don't put x and you don't put other numbers behind the natural log except for what is inside the natural log. This is the natural log of 3. If you somehow wrote it like this and say, oh, I'm going to do the natural log of 3 and it's times x, that's confusing. We don't know if you mean this is the natural log of 3 times x, or if you mean to say natural log of 3 times x, and those are two completely different expressions. So, to avoid any kind of ambiguity about this, you write the x in front. It's very clear that x is still a variable, and he is not inside the logarithm. The only thing that is inside the logarithm is 3. All right. Now, what you're going to see here is that we have x in two different places. And this could be a big problem. What we're going to do is play a trick that we see a lot of times in math classes. It would be nice if I could move these x terms together and combine and get something nice, but I can't because they're connected to things that don't add nicely together. One has a natural log of 3, one has a natural log of 7. And yes, I know these guys still just represent regular numbers, but I want to keep it as exact as possible for as long as possible. So what we're going to do is we're going to put everything that has x, put it on the same side of the equation, and if you don't have x, you go on the other side. Now, since 5 natural log of 3 is the only pure constant that I see, I'm just going to let him keep the left side as it is. I'm going to move this term from the left over here to the right side. All right, so this gives me negative 5 times the natural log of 3 equals x natural log of 7 minus x times the natural log of 3. Great. Both of my x terms are on the same side. The trick, so to speak, that we play here is that we do factoring. So you're never going to escape from factoring. And what I mean by this is that you have a common factor of x, both of those terms on the right side. So factor out the x, and you'll be left with natural log of 7 minus the natural log of 3. And now you only have one place where you have x. And this x is connected by multiplication to natural log of 7 minus natural log of 3. Again, that is just a number. So how do we get x by itself? We undo multiplication with division. So I'm going to divide both sides times, divide both sides by, I don't know why I said times, a natural log of 7 minus natural log of 3. So your final exact answer has negative 5 natural log of 3 in the numerator over the natural log of 7 minus natural log of 3. And as I mentioned before, this is exact. We haven't done any kind of rounding. We haven't lost any information. This is an exact answer. The next trick, or the next task, I should say, is coming up with a decimal approximation. That means, can you type this into your calculator correctly? Now, some scientific calculators are really difficult to work with. So there's one that I recommend. that has a nice 2-line display on it. So on the first line, you input your problem, you input your expression the same way you would on a graphing calculator. The second line is where your answer is going to show up. If you just have a single line scientific calculator, things are a lot more difficult. I mean, that's what I had when I was young, and I knew how to work with it because I used it all the time. But there are cheaper, better options out there. All right, so let's do this. All right, so I have -5 times the natural log of 3. Close my parentheses, right? Divide by, be careful. You're dividing by not just a number, but multiple numbers. So you have to open up parentheses to encapsulate the entire denominator. So we do the natural log of 7, close that natural log off, minus the natural log of 3, close off that natural log, and then do another set of parentheses to close off your denominator. And we come up with this answer that is about -6.4830. Now, this answer is, as a decimal, is not exact, but if we were to plug that into both of our expressions, we should have a true statement. So let's see how we would go about checking that out. All right, so store this by pressing the store button on your calculator, and then press the variable key. And when I hit enter, this is what my x is going to be representing whenever I type x on this calculate screen. Now, in our problem, let's just see what we had here. Our problem had on the left side 3 raised to the, make sure to do parentheses, x minus 5. Now, when I hit enter, it's going to give me a really, really small number, and it's probably even going to have like an E at the end representing scientific notation. Yeah, so again, really, really small number. That means you have the decimal point, and then you're going to have 5 zeros before you get to the 3320. Let's see if we get the same thing on the other side of the equation. 7 raised to the, this was just x. And you see we end up with the same value for both sides of the equation. So we have the right solution. Awesome. Now, granted, things can definitely get a lot more complicated than this. And it's just a matter of taking your time as you move pieces from one side to the other. All right. And again, one of the things you've got to really watch out for is using your parentheses correctly when you're typing things into the calculator. All right, so let's finish off with one more question here. And this is a question that, sadly, a lot of my students just leave blank. They go like, all right, I'm done. I can't do this anymore. All right, so let's do 23 raised to the 6x plus 13th power is equal to 37 raised to the 5 minus 2x. Okay, deep breath. First, recognize the kind of equation you have. This is an exponential equation because you have x's in the powers. And again, when you're writing this, make sure that you are clearly designating that 6x plus 13 and 5 minus 2x are powers. It's a superscript. Okay, so it's exponential. What do we do here? Well, first we try to identify if 23 and 37 have a base that's common, that we can build to get to 23 and 37. And we can't. 23 and 37 are both prime numbers, so they're not connected. All right, so that means we need to apply log on both sides so we can bring down those powers to contain our variables into a position that is more user-friendly. Now again, you have multiple pieces in the power, so you have to use parentheses here. So we have the group 6x plus 13 times the natural log of 23. On the right side, you will bring down the group 5 minus 2x times the natural log of 37. And then this becomes just like the last problem that we had. Natural log of 23 and the natural log of 37 are just numbers. And as such, we can distribute those. So we end up with 6x times the natural log of 23 plus 13 times the natural log of 23. On the right side, this is 5 times the natural log of 37 minus 2x natural log of 37. As we saw in the previous problem, we've got two instances of the variable x. So that means we have to get everybody to the same side of the equation. Well, sorry, everybody that has x on the same side. If you don't have x, you go on the other. Now, I kind of, as I really do a shortcut here, but I don't show everything. I'm going to mentally move this guy over to the left, and that's going to put all of the x's on the left side. Then I'm going to take the 13 natural log of 23 and move it to the right side to get all the constants over there. Now, when you're moving from one side to the other, you're just changing your signs. So this gives me 6x natural log of 23. This was a minus here on the right, so it becomes a plus as it moves to the left side. On the right side, we started with 5 natural log of 37, and then we're subtracting over the 13 natural log of 23. So minus 13 natural log of 23. Now, I want you to see right now that there's not a lot of arithmetic that we're doing. We're not multiplying or dividing or adding and subtracting to get big numbers. We're really just moving things around. We are reorganizing so that now, here on the left, we have all of our x's. And we can now factor out that common factor, give me 6 natural log of 23 plus 2 natural log of 37. And I know that that is not a very nice looking expression, but everything that's in parentheses is just a number. It's just some decimal, right? So we're going to divide both sides by this guy. So both sides divided by him. So both the left and the right side. I just have to make sure that I've transferred the numbers correctly from step to step. I don't want to change my 23 into 37 or vice versa. At the very end, we have x is equal to, not even approximately, it just equals 5 natural log of 37 minus 13 natural log of 23 over 6 natural log of 23 plus 2 natural log of 37. That is exact. But now we need to go to our calculator and come up with our decimal approximation. And again, this is where we have to be very, very careful about how we do things. You might even want to make little notes here and say, you know what? I've got to make sure that I open and close parentheses in both the top and in the bottom, because I have big groups I've got to worry about. And then I have all of these secondary parentheses that I'm going to have to take care of, otherwise my answer is going to be off. So let's come over here and let's type that in. Open parentheses for your big numerator. So we have 5 natural log of 37. Close the parentheses for the natural log, but you still have the big open one for being in the numerator. That's fine. Minus 13 natural log of 23. Again, the natural log opens parentheses, you close it. So I've closed the natural log. Now I need to close the numerator because I'm done with writing both of those terms. Divided by, Open up big parentheses for your denominator. 6 natural log of 23, close parentheses, plus 2 natural log of 37. Close the parentheses for the natural log, close the parentheses for your denominator. And let's see what we get. Okay. Seems fair enough, I guess. It's really hard to look at this and say, oh, well, of course, that's what the answer is. I was able to do the decimal work in my head. No, probably not able to do that. But let's do what we did before. Let's store this into our variable x. And then we're going to check both sides of our equation. On one side, we have 23 raised to the, now keep in mind, it's not just a single piece. It's parentheses, 6x plus 13. All right, I get 3.7 times 10 to the 10th power. So you're looking at something that's of the order of 37 billion. That's a lot. Well, let's check the other side here. 37 raised to the parentheses, 5 minus 2x. And I get an equally large number. All right. So everything checks out. I feel pretty good about that. And I hope that makes sense as we go through this step by step. Why are you doing this to me? It's being so weird. All right, yeah. So here are our answers, the exact value, and then we have the decimal approximation. So be very careful whenever you're typing things into your calculator. Do not do any rounding. Don't do any decimal stuff until the very, very end. All right. Well, I hope after watching this video, logarithms make just a little bit more sense. Again, it's just a different way of looking at an exponential expression. Just like with radicals, you know the power, you're trying to find the base. With logarithms, you know the base, and you're trying to find the power. All right. So until next time, I don't know that I'll be streaming tomorrow, seeing that that is New Year's Eve, a lot of fireworks, and my dogs get super freaked out, so I will be taking care of them. But we'll see. It might be a surprise one, you never know. But be safe out there. Please, especially if you're doing fireworks, do them safely, and be a good neighbor and clean up after yourself. Don't just leave the trash out there, because dogs and other animals may come and try to eat that stuff, and that's not good for them. Okay. So, take care, everyone, and have a good night.